Hello everyone, welcome to another lecture for drug delivery engineering and principles. So we have been talking quite a bit about particles in the last few lectures, and we are going to continue that discussion. So just a quick recap of what we learned in the last class. So in the last class we talked about liposomes, which we said are nothing but made up of phospholipids with a polar head group and a hydrophobic tail. And then there are several of them that gets aligned in a format like this, essentially making a hydrophilic core as well as a hydrophobic domain. Right. So, any of the drugs that are hydrophobic can get encapsulated in this region, whereas any drug which is hydrophilic can get encapsulated in this region, and this we talked about that these lipids are fairly compatible. They are actually derived from the cell phospholipids. And these could be several different types. This could be DPPC, DSPE. There are several types of lipids that are commercially available which people can use to make these liposomes, and you can get them to be charged, you can get them to be neutral, they can be positively charged, negatively charged. So all different variations are out there. So all of this gives a lot more tunability to liposomes than let us say some other particles that we have discussed, and that is why they are very widely used. Next we talked about stealth liposomes. So similar to the polymer drug conjugate that we had talked about a few classes ago, stealth liposomes can also be made by pegylating the external surface. Right. So you can have lipids that are conjugated to PEG or some other hydrophilic molecule, or you can have some conjugation chemistry taking place between the PEG molecule and the lipid itself to get this pegylation. And what that does is, again, it will act as a molecular windshield wiper. So it is going to continue to move in all directions and make sure that if any foreign protein or cell is trying to attack this particular liposome, it gets repelled away. So and that is the advantage, and we saw that similar to the polymer drug conjugates, when you conjugate PEG to these liposome particles, they have a very high residence time. So they can increase the residence time up to 10 times or higher. And then we talked about that these pegylation can also be in two different conformations. If it is fairly well covered and the surrounding density is very high between different PEG molecules, then these PEG brushes will tend to be close together and they can't really collapse because the other brush is not going to let it collapse. So they will essentially be in some sort of this brush conformation. Right. So it is like brush where all the bristles are sort of standing and making sure that there is really no space for the molecule to go into the liposome. Or what can happen is you can have them slightly far apart. So you can have a big PEG molecule, but then the density of the PEG is so low that it tends to collapse and sort of forms a structure like mushrooms. So if you see mushrooms are essentially you will find in the literature like this in the nature. So this is essentially that structure here, that these mushroom like structures have formed of these PEG brushes, and their surface coverage is not as high. So what can happen is potentially a protein can come in and is able to attack the surface of the liposome. So these conformations are not desirable if you are talking about repelling of any sort of foreign object from coming in contact with this liposome. So they do not work as well as let us say a brush conformation. So for most applications you would want a brush conformation to be present rather than a mushroom conformation. Okay, so we are going to talk further about another class of particles which is called micelle. Like liposome, they are also very similar. They also have hydrophobic and a hydrophilic domain. So you have a polar head group, and then you also have a tail which is hydrophobic. and unlike liposomes, these do not have a sort of bilayer that you saw. This is just a monolayer, and so there is no two domains, there is no hydrophobic and hydrophilic domain inside the particle, there is only a hydrophobic domain. So only the hydrophobic drugs can get encapsulated in this region, whereas the hydrophilic drug will have to be used by some other method. You have to use some other particle if you want to deliver hydrophilic drug. So this micelles is mostly for hydrophobic drug. So what are micelles? Micelles are nothing but these are aggregate of amphipathic molecules in water with non-polar portion which is inside, which is of course hydrophobic, and the exterior is exposed to polar head groups which are hydrophilic. So if you put any so these are essentially sort of detergent like molecules which have both hydrophilic and hydrophobic domains, and although they are not as hydrophobic as the liposome lipids are. So if the lipids are extremely hydrophobic and they have a very long hydrophobic domain, then they tend to form liposomes, and if they are not as hydrophobic, they have some solubility in water, then they tend to form micelles. So these amphipathic molecules will form micelle above a particular concentration, so which is called a critical micellar concentration, CMC. So for any sort of amphiphilic molecule, there is a CMC that is defined. This could be let us say 1 mg per ml, this could be 1 microgram per ml, or this could be something else. But for any amphiphilic molecule above these particular concentrations, they will tend to form micelles. Below that, they will be in the solubility limit. So they will still be soluble, but as you increase the concentration of these molecules in the water or the aqueous environment, they will tend to then form these micellar structure. And as you can see from the structure itself, these are essentially talking about single molecules and maybe 5-6 of them at a length. So micelles tend to be fairly small, typically less than 50 nanometer, and they are formed from single chain surfactants. So as I said, most of these surfactants are single chain. If they are double chain surfactants, then their hydrophobicity is fairly high and they tend to form liposomes. But if they are single chain like we have seen in this figure, then they tend to form micelles. So that is somewhat a distinguishing feature between a micelle and a liposome, and of course we talked about that liposome can carry both hydrophilic and hydrophobic drugs because it has two different domains inside the particle, whereas in micelle you only have one single domain which can only carry hydrophobic drugs. You can potentially still conjugate the drug on the surface, and so that way it can allow you to carry hydrophilic drugs as well, but predominantly if you are looking for encapsulation and all those kinds of things, then you have to look at hydrophobic drugs with micelles. So as I said, the hydrophobic drugs can be encapsulated or solubilized in the inner core. So another major difference between micelle and liposome is the size itself. So as we discussed, the liposomes you can make them anywhere from 100 nanometer to all the way up to a few microns, whereas in micelles because they are formed by self assembly and this very small molecules that we are looking at, typically the size of the micelles is small and they are below 50 nanometer. So around 10 to, typically you will find them in the literature to be about 10 to 30 nanometer. Okay. So now that we have studied these effect of different types of particles and their properties and how to sort of make them, let us talk about particles in general as to what is the different features of a particle that we can think of. So one thing that immediately comes to our mind was size, and we discussed about size as we went through all different things. We talked about emulsion based methods in which we can vary the size depending on what amount of power and what amount of concentrations we are using. And then we talked, and then the other thing that comes to mind is the particle shape, right. So so far most of our discussion we have talked about is spherical particles, but if you look at the nature, you will find that not everything is spherical. So you have different spiky kind of viruses, you have bacteria which are rod shaped, you have bacteria which are spherical, you have our RBCs which are essentially disc shaped particles, and they have actually evolved over millions of years of evolution to maintain this shape, and this shape also confers some advantages. So then the idea is that can we sort of mimic this property of the shape from nature and see if that can help us in various applications of drug delivery or tissue engineering in terms of getting more efficacy and patient comfort. So, so this is basically the motivation to vary the particle shape, and of course we see in the nature also. So, why do RBCs are disc shape? So, typically when a spherical particle flows through a vessel, what you will find is in a streamlined motion it will continue to go straight. So, if a particle is going straight, it will continue to go straight, it will not really go towards the edge of the vessel. But then what is the main job of RBC? The main job of RBC is to deliver oxygen. So, if it wants to deliver oxygen, it wants to be closer to the surface. So, what it has been found, if the particle is non-symmetrical, that is non-spherical, and let us say if a particle instead of being a sphere, this is a rod shaped particle, then it tends to tumble around as it flows, and because of this tumbling it is now exploring the blood vessel in quite high quantities, and that way it can then deliver oxygen at a much better efficiency than let us say a spherical RBC. So, that is why we see that different sort of natural particles are of different shapes depending on what their role is in the nature, and that is over a million of years of evolution that they have acquired that particular shape. So, again as I said, for bacteria non-spherical shapes also offer a large contact area with the surface. So, if I say that I have a surface onto which if I seed a spherical particle, the contact area is essentially this little point right here, whereas if I am seeding a rod shaped particle, you have a much higher surface contact, and so it will help this bacteria to adhere to the surface also better. Also the rod shape also gives faster mobility to the bacteria, and we talked about disc shaped particles being able to marginate in the blood vessels quite a lot. So, there are obviously some advantages of shape, and then because of this we also want to explore what are some of these concepts that we can then sort of pick and use it in our drug delivery vehicles, so that we can do a better efficiency of drug delivery as well as much more controlled delivery. So, let us see. So, how do we make different spherical shaped particles? So, there are several reports in the literature actually. Shape has been more and more sort of considered as a paradigm that can be varied and can be used for different applications. So, here are just some examples of different shape of particles, both nano and micro, that have been formed. So, you can you name it and there is shape for it. There are spherical particles, there are spherical particles aligned in a certain pattern. There are these rod shaped particles or ellipsoidal particles, you have these cone shaped particles. So, there are all kinds of particles that have been synthesized by researchers across the world, and it has been studied and actually shown in certain applications that these shape can actually play an important role in sort of increasing the efficacy of delivery. So, how do you make them spherical? So, the thing is, if you are going to use any sort of chemical methods, what happens is due to the surface tension of the water and the minimization of the contact area between different oil and different fluid, it always tends to be spherical. So, somehow we got to mitigate that. So, there are two approaches which you can use to make spherical particles or non-spherical particles. One is you can use a bottom up approach, which basically means you do some chemical reaction, you grow a particle right from this individual atoms into a bigger structure up to what you want. Or you can do a top down approach, as you have a big particle and then you break that down into smaller particles or somewhat synthesize the particle immediately in a size that you want. So, let's look at it. So, here is a group from Samir Mitra Gotri, which are using polymeric micro and nanoparticles of complex shape, and so the way they have done this is they have, in this case, in this particular paper, they are using a polystyrene polymer. And what they have done is they have made a mold of PVA. So, this is a PVA mold, another polymer, which essentially they have created a film and embedded these polystyrene beads, which are spherical. So, you can synthesize them and you can buy them directly from commercial sources. So, what they have done is they have entrapped these polystyrene beads in the PVA mold. And then what they have done is they have heated it above the melting temperature of the polystyrene. So, polystyrene if you heat it up to let us say 95 degrees Celsius, it will start to melt. So, now what you have is you have a PVA mold, and in that PVA mold there are cavities which contain polystyrene in liquid form. Then what you do is you apply force on polystyrene mold on, let us say, a single dimension. So, once you do that, what is going to happen is because now this force is there, you will have expansion of these pores in one direction, and hence create an anisotropy in the system. And because this is liquid is going to fill up these pores, and then you can cool it down, cool down to room temperature, and what will happen, you will now have a polymerized polystyrene which is of a ellipsoidal shape, right. So, that is one of the methods that they have used to make these different shape particles. You can have a different scheme too, you can first stretch it. In that case you still have a solid polystyrene, so it is not going to flow, and then you heat it. So, what will happen, because you have heated it later and you only heat it for a certain amount of time, you only get certain filling of these pores, and then you cool it back again, and now you get a different shape. Now you are getting a shape which is more looking like sort of a tabla, for example. So, so just by imagining how you do this and how you are stretching this, of course this is just one dimension I have shown stretching, you can stretch it in the other dimension as well, the x and y as well as the z direction as well. So, all of these can be done, and you can stretch it in all three directions in different ratios, and all of this will result in different configuration of the particles that will end up being made through this PVA mold. So, these group then went ahead and did this in different dimensions, and now you can see they get all types of shapes here. They have a fairly spherical shape, they have sort of pancake kind of shape, they have shape like worms, they have shape like long rods. There is some sort of a UFO like object. So, depending on how much they are stretching at various dimensions and various axes, they can get all kinds of different shapes. So, this is just one example of how you can sort of get these different shape particles. Another way you can go is the top down approach, as I was saying, is to sort of build it. So, an example I will give you is from this paper that was published in ACS Nano in 2012. And what it is these guys have used an imprint lithography tool. So, it is a fabrication tool that is currently used for LEDs and hard drives manufacturing. And what they have done is they have a silicon wafer. So, they have a silicon wafer, and then they have a quartz template which already has these shapes that they want etched into it. So, you can get this through some ion beam etching and all, we are not going to go into details for that, but you have some templates with predefined shapes. And then you have some sort of a sacrificial layer which is spin coated. So, you have a small let us say 10 micron, 20 micron thick layer which is called a sacrificial layer, and we will talk about why it is called a sacrificial layer, but it is something that can be dissolved in a certain solvent. So, then what you do is you dispense your pre-polymer solution that you want to make these particles out of. You come down with a quartz template. The reason the quartz template is used is quartz is fairly transparent to UV wavelengths. So, you come down, what will happen is due to the Kepler reaction, all these cavities that were present in the quartz template will get filled. So, now you essentially have a structure where all these cavities have been filled. Then you come down and shine UV. The UV causes the polymerization of this liquid. So, once it is polymerized, now they will maintain the shape because there is a structure to it now. Then you can just take the template away. Now, you have these small standing structures which are all connected, by the way, with the extra fluid that was there. So, it has created sort of a film with some structures on it. And then you can come with a very directional high energy plasma or something to sort of etch this away. So, what will happen is this top portion will get eroded away, this portion will get eroded away, and the portion that was below the particle will become a part of the particle, and you get freestanding structure over your sacrificial layer. So, this remember is a sacrificial layer. Okay. And then you can just come in with whatever solvent the sacrificial layer is soluble in, let us say water, and that way the sacrificial layer will dissolve and you will have particles in the suspension. So, these authors then went ahead and used this method. In this case, for the pre-polymer solution, they have used a hydrogel based system. So, this is essentially nothing but hydrogel, and what they have is they have a PEG with a diacrylate, and then they also have a peptide which also is a diacrylate, and I will come back to the peptide again. But what will happen if you shine UV with some initiator, let us say they have added an initiator, then what will happen, the initiator will start a free radical reaction, there will be a radical form, and acrylates as we know can react with another acrylates using a free radical reaction. So, this will result in a polymer network being formed. So, this is just one unit, but essentially there will be several units of this polymer and so on and so forth, which all have, if you mix them in a 50-50 ratio or a 25-75 ratio, depending on what ratio you have, you will end up getting this peptide also sort of cross linking the polymer itself. And now this peptide itself is degradable by certain proteases, let us say cathepsin B. So, cathepsin B might be upregulated in a disease. So, we know some of the cathepsins are upregulated in cancer. Right. So, because it is upregulated in cancer, once these particles reaches a cancer site, they will degrade faster compared to any other site. So, if your drug which was also added at the time of pre-polymer solution is encapsulated within this network, then what will happen is once it reaches the cancer site, more and more drug will come out at the site, and that way you will have a lot more efficacy of your particles because it is responsive to the cancer tissue. So, these groups have then went ahead and made different shapes of particles. So, essentially all these shapes are defined by the template shape itself. So, depending on what shape you etched in the template etching pattern will essentially define what shape you end up getting, and that way you can get all kinds of shapes that you want in a very nice array that is being shown here. And then the group then further showed that if you treat that with, let us say, cathepsin B, as I said that these networks are susceptible to cathepsin B degradation because cathepsin B is going to cleave the peptide. So, what you see is over time as cathepsin B is incubated, ultimately all the particles are gone, they have degraded, and in this case they have shown that there was some DNA or some antibody that was encapsulated within this polymer network, and when they have added the cathepsin B, before addition of cathepsin B there is very minimal release or no release at all, and once they have added cathepsin B, quite a bit of amount of the polymer or the drug has released. And then you can get these individual particles. This is an SEM image showing the particles by themselves of all kinds of sizes. You can get various drugs in these particles. So, this is showing different drugs that are being encapsulated. So, you have in this case you have encapsulated some antibody, but the group has also shown encapsulation of doxorubicin or any drug that might be relevant for certain application. So, this is just a fluorescence image, and then you can do an uptake with the cells to see if I want to deliver things to mammalian cells, how do mammalian cells then take these things up. So, the group has used several different cell lines. So, in this case they have epithelial cell lines, 2 of the epithelial cell lines and one dendritic cell line and another endothelial cell line. And what you see is that different shapes, even though they might be of similar volume. So, in this case this smaller disc and this smaller rod are equal volume. Similarly, this larger rod and this larger disc are of equal volume. So, even though they are of equal volume, you see that their amount of uptake in the cell is very different, and because everything else is same, the material is same, the charge of the particle is same, since the same material, the volume of the particle is same. So, essentially the size of the particle is same, the only thing that is different is the shape. So, the authors were able to conclusively say that because of a certain size or a certain shape, a certain geometry, you get a difference in the uptake. So, certain shapes are better for delivery to the cancer cells or epithelial cells in this case than say others. And what you also found is very interesting is for let us say epithelial cells and dendritic cells, you have the same trend. However, endothelial cells do not really follow this, right. If you notice, so all the discs have been shown in red. In all the 3 cell lines you see that the red is above the rods. However, this is not true with endothelial cells where it does not seem to be much different. So, what not only the shape will help you to get more in the cell, what it also does is it also makes it selective. So, let us say if you want to target epithelial cells, you may want to use the disc shaped particles, whereas if you want to target the endothelial cells, you may want to use some other sort of particles and not maybe disc shaped particles. So, this was a fascinating result, and then further to that they further looked into what mechanisms are causing this, and what they found using by different inhibitors. I am not going to go into details of what these inhibitors do, but essentially the cells have different pathways through which the particles are uptaken, and all of these inhibitors inhibit some of these pathways, and what they find is that different shape particles get uptaken by different mechanisms. So, if you look closely here, you find that disc shaped particle uptake is affected when Philippine is used, whereas it is not affected for the rod shaped particle. So, it also shows that there is another mechanism through which disc shaped particles are going in the cell. So, I guess the crux of the matter from all this is shape can play a very important role, and it should be considered when we are talking about drug delivery and all. Here is another example of how shape can play a role. So, this is essentially a cancer tissue. So, we know in cancer there are limited blood vessels. So, there is diffusion limitations from the blood vessel. So, let us say if I am delivering a drug, it may not be able to go far away from the blood vessel, right. So, let us say if a drug is coming out from these vessels and then it has to now diffuse all the way to the farthest cell away from the blood vessel. So, this is just a pictorial representation of a real example where you have delivered 150 nanometer particles which are labeled as green, and the cancer is being labeled by collagen as red. So, what you see is here is a blood vessel, and what you see is all the particles are essentially localizing near the blood vessel itself, and as you move further away the amount of particles is decreasing. So, this is a big limitation. So, another group tried to explore the use of shape of particles to see if the diffusion is better. So, can the shape improve the penetration inside solid tissues? So, what they did is they used an in vitro tissue model called spheroid, which is essentially nothing but aggregation of cells which are avascular. So, you can then consider that there is a blood vessel running right across this spheroid, and anything, because this is essentially medium, anything which is further going in is away from the blood vessel. And what the group found is that again the disc shaped particles were able to penetrate quite a bit deep into these tissues, even though the same sized rod shaped particles do not do as well. And this is just a quantification showing that yes, in different regions further in from the blood vessel, you get further and further increased amount of penetration of certain particles. Okay, so we will stop here, and we will continue about further discussion on the particles in the next class. Thank you.